Now I want to give an idea of the proof of theorem A. So instead of theorem A, that might be a little bit too ambitious, I will sketch the proof of a simplified inequality, which is theorem A prime. So we start again with an n-dimensional complete asymptotically Euclidean spin manifold. We assume that the scalar curvature is non-negative, and we assume that the manifold has compact boundary. And we suppose again that x0, x1 are codimension zeros on manifolds with boundary, such that these inequalities are satisfied. Moreover, we require x0 to contain all asymptotically Euclidean ends of x. Moreover, we assume that the scalar curvature is greater or equal than kappa n times n minus 1 on x1 minus x0 for some positive constant kappa. And now we define d to be the distance between the boundary of x0 and the boundary of x1, and L to be the distance between the boundary of x1 and the boundary of x. And then I want to show that there exists a constant R depending only on d and kappa, such that if L is greater than R, then the ADM mass of x must be positive. Now, since the Riemannian manifold M is spin, then we can associate to it the spinor bundle that we denote by S, and the Levi-Civita connection on S, and the Dirac operator. So the Dirac operator acts on smooth sections of the spinor bundle, and it is a first-order elliptic differential operator. The Dirac operator is related to the scalar curvature of G through the classical H-Norris formula. So here is the square of the Dirac operator, nabla star nabla is the connection Laplacian, and the second term is the curvature term. So I will now quickly review Witten's argument to proving the positive mass theorem. So we consider the following geometric setting. Let M be a complete n-dimensional asymptotically Euclidean spin manifold, and suppose that E is a selected asymptotically Euclidean end with a chosen asymptotically Euclidean coordinate system x1, xn. Suppose that U0 is a smooth spinor on M, which is constant of norm 1 at infinity in E with respect to, of course, our asymptotically Euclidean coordinates, and such that U is equal to 0 in all other asymptotically Euclidean ends on M. Then there exists a spinor U1, such that U1 over rho is in L2. So remember that rho is the radial coordinate in our chosen asymptotically Euclidean system of coordinates. And the second property is that the U1 is equal to the U0. So this actually, these two properties follow from the analysis of the spinor Dirac operator on suitable weighted Sobolev spaces. Now define U to be U1 minus U0. Then we directly have that du is equal to 0, and by direct computation, we have that the mass of the selected end is proportional to the following integral. And here actually is where the H-Norris formula is used. Now, since the u is equal to 0, then this term cancels out, and moreover, this term is greater or equal than 0, and therefore, if the scalar curvature is non-negative, then the ADM mass must be non-negative as well. Now we want to perturb Witten's method by adding a potential. So we say that a smooth function psi from M to R is an admissible potential if psi is equal to 0 in a neighborhood of infinity. So here M is still a complete asymptotically Euclidean Riemannian spin manifold. Consider now the Dirac bundle E, just S plus S with Dirac operator P, which is defined by this formula. Moreover, consider the bundle map sigma, defined by this formula. For an admissible potential psi, we define the associated Cayley's operator B psi, which is just P plus sigma psi. So this is a first order elliptic differential operator acting on smooth sections of the bundle E. Moreover, its square is given by this formula. Now, a variation of Witten's argument yields a section U of E such that B psi U is equal to 0, and the ADM mass is proportional to this integral. Now, this is actually nabla is actually the connection on S plus S. Now, this second term is going to be 0 because of this condition. And the first term is again non-negative. And therefore, now we found a new condition, that is, if this expression is non-negative, then the mass must be non-negative as well. We have exactly this conclusion. Now, the advantage here is that the scalar curvature is allowed to be negative in a certain compact region. So in other words, we allow, let's say, a compact well of negativity for the scalar curvature, as long as it is compensated by the other two terms, by psi squared minus d psi. Actually, in our application, we consider the case where the scalar curvature is negative in a region when the potential is constant. So in the end, the negativity of scale G will be compensated by the positivity of psi squared. So now let's get back to theorem A prime. So remember that X is a complete asymptotically Euclidean spin manifold with compact boundary, and we have our codimension zero submanifolds with boundary such that these inequalities are satisfied. Moreover, we assume that there is a positive constant kappa such that the scalar curvature is greater or equal than kappa n times n-1 on x1 minus x0, and the scalar curvature is non-negative globally. Now, d is the distance between the boundary of x0 and boundary of x1, and L is the distance between boundary of x1 and boundary of x. Now here we start with a manifold boundary, which is complete and asymptotically Euclidean. So the idea is that we want to double it and then reduce to the perturbed Witten argument that I just described. Another observation is that in order to do that, it's enough to assume that there exists a constant R, depending only on D and kappa, satisfying the following property. So if L is greater than R, then there exists a color neighborhood U of the boundary of X, such that for every t greater than 0, there exists a function psi t from X to 0t, satisfying the following properties. So psi t is equal to 0 near infinity, psi t is equal to t in the color neighborhood U, and moreover, psi t satisfies the following differential inequality. So in particular, this condition is needed because we want to construct an admissible potential on the double. This condition actually is needed because in order to double the manifold, we want to modify the metric in a small scalar neighborhood of the boundary, and then we want to be able to control the negativity of the scalar curvature. We start with our asymptotically Euclidean Riemann manifold boundary. Of course, so this is your neighborhood U, and near the boundary, the metric is arbitrary. Now we change the metric near the boundary, and we make it a product. Now, by doing so, of course, we cannot hope to keep the positivity of the scalar curvature. So in other words, the scalar curvature might become very negative. However, by choosing t large enough, we can assume that t squared always dominate the scalar curvature of the new metric. I notice that U is a compact set. Now we pick psi t satisfying properties 1 to 3. And now we can finally double the manifold X. And then in this way, we obtain a manifold M, which has the property that now is complete and asymptotically Euclidean. Moreover, we extend psi t to the double, and then using property 1, 2, and 3, we obtain that this condition is globally satisfied over the Riemann manifold M G tilde. And now we use using the perturbed Witten's argument, we deduce that the mass of each end must be non-negative. So finally, I want to explain how to construct such a potential. So why does it exist a neighborhood with this property? All right. So here is a sketch. So we start with boundary of x0, boundary of x1. This is our D. Remember that on x1 minus x0, so on this region over here, we have that the scalar curvature is greater or equal than a certain constant kappa. We can pick a function psi, which is 0 on this region and is 1 on this region. And now, of course, we can scale it down with lambda. So at the end, we will find a function such that this differential inequality is actually greater or equal than 0. Now we want to construct a function. We want to extend psi into the region over here. In this region, we only know that the scalar curvature is greater or equal than 0, and therefore this differential expression is going to be greater or equal than psi squared minus the psi. But then you just assume that you just take psi to be a function of the distance from the boundary of x1, and then you solve the equation psi squared minus the psi equals 0, psi 0 equals lambda. So lambda is the number that we achieved with the potential of the blue region. And then the solution, of course, of the differential equation is the function lambda over 1 minus lambda s. And this function blows up at the point s equals 1 lambda. And now if I take this number to be L, then I obtain that if the distance from the boundary of x1 and L, so in other words, if the boundary of x1 is over here, then I can always, for every constant t, I can construct a function. Okay, the way I construct it right now is just a Lipschitz function, but it's not difficult to show that actually you can take a smooth that achieves, since this blows up at 1 over lambda, a function that achieves any number t, and then becomes constant in this neighborhood U. Okay, so this is all I wanted to talk about. Thanks a lot for your attention.